Imagine you're standing at the edge of Yellowstone National Park, where steaming geysers erupt like Earth's impatient sighs, and vast calderas whisper of cataclysms long past. This isn't just a scenic wonder. It's the scar of a supervolcano, one of the planet's most explosive secrets. But what fuels these behemoths? What hidden force stirs the magma that could blanket continents in ash? Today, we embark on an extraordinary voyage, journeying inside Earth's mantle plumes, those fiery pillars suspected of being the very engines of supervolcanoes. Buckle up, because we're diving deep, deeper than any human has gone, into the molten heart of our world. Let's start with the basics. Earth isn't a static rock. It's a dynamic beast, layered like an onion forged in hellfire. At the surface, we have the crust, a thin skin of rock just 5 to 70 kilometers thick, depending on whether you're over ocean or continent. Beneath that lies the mantle, a colossal shell stretching 2,900 kilometers down to the core. This isn't the fiery liquid you might picture from movies. No. The mantle is mostly solid, composed of peridotite, a dense mix of silicates under crushing pressure. But here's the twist. It's hot, scorching up to 4,000 degrees Celsius at its base, and it flows ever so slowly, like ultra-thick honey over eons. This sluggish dance is convection, driven by heat from Earth's radioactive decay and the lingering warmth of its formation 4.5 billion years ago. Hotter material rises, cooler sinks, creating currents that sculpt the surface. Most volcanoes, like those ringing the Pacific's fiery rim of fire, owe their fury to plate tectonics, the grinding of crustal plates that melt rock where they collide or pull apart. But supervolcanoes? They're loners, erupting far from plate edges, spewing over 1,000 cubic kilometers of material in a single cataclysmic blast. The culprit, scientists propose, is mantle plumes. Narrow columns of superheated rock rising from the deep mantle, punching through the crust like geothermal geysers on steroids. The idea of plumes dates back to the 1970s, when geophysicist Jason Morgan suggested they originate at the core-mantle boundary, that razor-thin divide 2,900 kilometers down where the liquid outer core meets the solid mantle. Picture it. Iron-rich molten metal sloshes against ancient, cooler rock and blobs of primordial material. Remnants from Earth's violent birth, heat up and buoy upward. These plumes are narrow, maybe 100 kilometers across, and they rise at a leisurely 10 centimeters per year, carrying heat and chemicals that melt the overlying mantle into magma. But are they real? For decades, skeptics argued plumes were myths, mere illusions from uneven heating. Then came seismic tomography, the CT scan of Earth's interior. By analyzing earthquake waves as they ripple through the planet, scientists map density variations, low velocity zones, cooler and slower to transmit waves, trace plumes like ghostly fingers. Under Hawaii, the classic hotspot, a plume fattens from a thin pipe at depth to a bulbous head near the surface, fueling the island chain as the Pacific plate drifts over it. Similar signatures lurk beneath Iceland, the Reunion Islands, and yes, Yellowstone. Now, let's ignite our journey. Strap into our imaginary submersible, a vessel of pure science, impervious to pressure and heat. We breach the crust at Yellowstone, slipping through fractured basalt laced with hydrothermal vents. The air, the rock, grows denser. The temperature climbs to 1,000 degrees. We're in the lithosphere, the rigid outer shell, but soon it yields to the asthenosphere, the mantle's ductile underbelly, where rocks deform like warm taffy under stress. Descending further, the pressure mounts, millions of atmospheres squeezing us like a cosmic vice. At 400 kilometers down, the transition zone appears, a buffet of mineral phases. Olivine morphs into spinel, ringwoodite hoards water like a sponge, up to 1% by weight. Enough to fill oceans if squeezed out. But we press on, into the lower mantle, where bridgmanite dominates, a high-pressure perovskite that locks up most of Earth's magnesium and iron. Here, 1,000 kilometers deep, the heat intensifies to 2,500 degrees. Our plume emerges, a roiling updraft of hotter, less dense material, glowing with infrared fury. It's not uniform. Seismic images reveal undulations, pulses of magma rising in rhythmic surges like the heartbeat of a slumbering giant. Recent studies from 2025, peering beneath Africa's East African Rift, detected just that. deep pulses of molten rock ascending every few million years, cracking continents and birthing volcanoes. These aren't random. They're tied to the plume's buoyancy, instabilities rippling upward from the base. Deeper still, at 1,500 kilometers, we encounter the enigmas, the blobs. Not the cute animated kind, but large low shear velocity provinces. Two continent-sized anomalies, one under Africa, the other the Pacific, lurking at the core-mantle boundary. These aren't just hotspots, they're thermal insulators, possibly piled up subducted slabs or primordial reservoirs from the moon-forming impact. A July 2025 study in Nature Geoscience linked them directly to supervolcanic outbreaks. By modeling mantle convection over 1 billion years, researchers showed plumes spawning from the African blob's edges, migrating with the plates, and triggering massive flood basalts, the lava floods that pave provinces like the Siberian Traps, culprits in history's worst mass extinction. Our submersible weaves through the plume's core, where temperatures spike to 3,000 degrees, melting silicates into basaltic magma rich in iron and titanium. Chemicals hitch a ride too. Enriched in rare earth elements, they isotope fingerprint the eruptions above. As we near the core-mantle boundary, the pressure hits 136 gigapascals, 1.36 million times sea level. Iron-nickel alloy churns below, generating the magnetic field that shields us from solar wind. But updraft wins. Our plume, born here, carries chunks of this exotic brew, seeding surface diversity. Emerging from the depths, virtually of course, we resurface at a supervolcano's doorstep. How do these plumes ignite apocalypse? When a plume head swells upon nearing the base of the lithosphere, it ponds, melting vast swaths of mantle. Magma chambers balloon beneath the crust, fracturing it into a cauldron. Pressure builds until, boom! The eruption isn't a cone's polite puff. It's a caldera collapse, the roof sinking as 2,500 cubic kilometers of rhyolitic ash and pumice explode skyward, dwarfing Mount St. Helens by 1,000-fold. Yellowstone's last super eruption, 640,000 years ago, coated half the U.S. in ash, dimming the sun for years. Its plume, tilted by plate motion, now feeds a chain of older calderas stretching into Nevada. Similarly, Toba in Indonesia, 74,000 years back, nearly bottlenecked humanity. And the Deccan Traps, that plume-driven lava flood 66 million years ago, may have smoked out the dinosaurs. Statistics from a 2025 University of Wollongong analysis confirm it. Over 80% of ancient giant eruptions align with plume paths predicted from blob models, a smoking gun for the plume hypothesis. Yet debates rage. Some geodynamicists favor edge-driven convection, plumes from the sides of upwellings, not the core. Others point to ghost plumes, like one discovered in June 2025 under Oman. A deep upwelling with no surface volcanoes, perhaps starved by thick Arabian crust. And in the Pacific Northwest, axial seamounts Hotspot plume is rumbling. Earthquakes spiked in April 2025, hinting at an underwater eruption soon. These nuances remind us, Earth's engine is chaotic, unpredictable. As we conclude our descent, consider the implications. Mantle plumes don't just sculpt landscapes, they reshape life. Their next pulse could awaken Yellowstone, though odds are slim, 1 in 730,000 annually. Monitoring with seismometers and satellites grows sharper, but the deep remains mysterious. Plumes teach humility. Beneath our feet, forces birthed mountains, oceans, and us. If this journey ignited your curiosity, hit subscribe for more dives into Earth's wild side. What deep secret should we explore next? Drop it in the comments. Until then, keep looking down. Wonders lurk below.